Hello everyone, this is Leela from CSCR. So today I'm going to present on register allocation and assignment, an important concept in compiler design. Register allocation is a key phase in compiler design. During intermediate code generation, the compiler assumes unlimited variables, but in real systems we only have limited CPU registers. So the compiler must map many variables to few registers efficiently. This directly affects performance because poor allocation increases memory access and slows down the program. Registers are small storage locations inside the CPU. They are faster memory with access time around 1 clock cycle. They are much faster than RAM. They store intermediate results and frequently use data, but they are limited in number, usually between 8 to 32 registers. Here the diagram shows the memory hierarchy. At the top, the CPU registers, which are fast. Below that is cache, the main memory, and then the secondary storage. As we go down, speed decreases, and access time increases. This is why using registers improves performance. The 8086 architecture has two main units. Bus interface unit, which handles communication with memory and input-output. It fetches instructions. It stores them in a prefetch queue. And then there is execution unit. It executes instructions and it contains ALU and general purpose registers like AX, BX, CX, and DX. EU processes instructions but doesn't directly access memory. 8086, here the diagram shows how BIU unit and EU unit work together. BIU fetches instructions and sends them to EU. EU performs operations using registers and ALU. This coordination improves execution speed. Programs use many variables, but registers are limited. We cannot store everything in registers, and accessing memory is slow. So we try to keep important variables in registers. The goal is to reduce memory access and improve execution speed. Yeah, this slide shows the compiler phases. Lexical analysis, first there is lexical analysis, and there is syntax, and there is semantic analysis. And after that, there is intermediate code generation and code optimization and register allocation. And at last, there is machine code generation. Register allocation is an important stage before final code generation. Liveness analysis checks whether a variable will be used later. If not, it is considered dead. Interface occurs when two variables are live at the same time. Such variables cannot share the same register. So liveness identifies the active variables and interface shows conflicts. In this method, each variable is a node and each register is a color. If two variables interfere, they are connected by an edge. So the rule is connected nodes cannot have the same color. If we can color the graph with the available registers, allocation is successful. Otherwise, some variables must be stored in memory. Linear scan is a faster alternative. It processes variables sequentially using live intervals. If a register is available, assign it. If not, spill a variable to memory. It is fast but slightly less optimal than graph coloring. After allocation, register assignment maps variables to actual registers. It considers CPU limitations, instruction requirements, and function calls. It also tries to reduce unnecessary operations. Yeah, in this example, variables are assigned to registers. Operations like mov, add, and move, add, and sub are used. The goal is to reuse registers efficiently and minimize the memory usage. When registers are enough, spilling occurs. So variables are moved to memory. This requires extra load and store operations, which slow down execution. So compilers try to minimize spilling. Register allocation is used in real systems like GCC and Clang, Java Virtual Machine, and JavaScript engines. It can improve performance by 10 to 30%. So to conclude, register allocation maps variables to registers, uses liveness and interference. Methods include graph coloring and linear scan. Spilling occurs when registers are limited. Efficient allocation leads to better performance. Thank you.